Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Kiersten Boley with us today. Hey, Kiersten.
Hi.
How are you doing today?
I'm doing great. How about you?
I'm doing awesome on the 16th of May, 15th of May. 2023 as we record this. And I'm in Phoenix. And Kiersten, where are you located at?
I'm actually in Columbus, Ohio.
Columbus, Ohio. Very cool. So we're in that one. What's your position there?
So I'm a grad student at The Ohio State University, and I'm actually going to be graduating next year, which seems like really soon. But yeah.
Because it takes a while to actually put the thesis together to satisfy all the micrometer folks, you know?
Yeah, this is true. I feel like I'm trying to put the thesis in the back of my mind, though.
It will come to the front. Well, I really look forward to saying Dr. Boley. Welcome. Thank you.
Yeah.
Very cool. Very cool. Let's see. And as part of that research and putting on your thesis, what kind of research do you like to do broadly?
Yeah, so I actually like to dabble in two different sorts of things, kind of looking at the big picture as well as the smaller inner workings of things. And what I mean by that is I like to look at how elemental abundances impact planet formation, as well on a statistical level, as well as looking at how we can use that information for planet interior modeling.
Ooh, nice.
Yeah. So it's a lot of fun. So two very different topics, but they're very much linked.
Yeah, very cool. Very cool. And we're going to see part of that in this very awesome AJ article.
Yeah.
And it's open access, people. We're in the open access area. You can go grab a copy for free. Go get one. Searching for transiting planets around halo stars. 2, constraining the occurrence rate of hot Jupiters. And Kiersten, take us away.
Yeah, so this paper was done by me and a whole bunch of my lovely collaborators. So I work with Professor G. Wong, Joel Zinn. He was a postdoc at the time at CFA. And so he's been great, as well as some other collaborators that really helped with some follow-up observations, which we'll get into in a little bit. But generally, this paper is looking at this idea of how much material is required to form a planet. And one of the reasons why we would look at specifically halo stars is because they're some of the oldest and most metal poor stars in our galaxy. So yeah, and another reason why we would consider metallicity, specifically looking at iron to hydrogen ratio, is because we know that for these Jovian type planets that they have this strong metallicity correlation. And in fact, we were able to see this from the first 4 planets that were ever discovered. We were able to see this really strong correlation with metallicity. Cool. And so the idea here is that we expect that there's a particular point at which planet formation begins or cuts off, whichever way you want to think about it. And this is because we need a certain amount of material to form a planet. If you don't have that material, you're not going to form your planet. And we haven't observationally seen where that is exactly. So this is kind of the motivation behind this work, looking at these extremely metal poor stars so that we can start to try and answer this question. And specifically, we looked at this using TESS observations. So we wanted to use TESS as opposed to Kepler because we're able to get a significantly larger sample of these metal poor stars, whereas Kepler was looking at a particular area, a tiny little area within the sky. TESS, since it's basically an all sky survey, we get to see a ton of different stars. And so it seemed like the perfect time to really start to try and answer this question: when does planet formation begin?
Yes. Good. Very awesome.
Yeah.
Okay.
Yeah. So what we did, and this is kind of where the part 2 comes in to this paper,
Okay.
is we ended up forming this sample of around 17,000 halo stars, and that's in paper 1,
Okay.
where we were able to basically make a couple of different cuts. So one of the cuts that we ended up making to ensure that our stellar population was actually halo stars is we did a velocity cut. So
Okay.
basically anything that was above a particular velocity, we were able to say with some pretty good confidence that these are not in the thin or thick disk.
Okay.
And so yeah, so we made that cut. And then from there, we were able to do this population study, because not all of those stars, as you can imagine, had spectroscopically derived metallicities.
Yeah.
And you really want that when you're doing something that kind of relies on that. So, yeah, so we ended up doing this population study, and basically we found out that a large portion of the actual stars within our sample were A, halo stars for sure,
Okay.
and B, they were really metal poor. And to give you an idea of that population study that we did, the median metallicity was around negative 1.2
Okay.
metallicity, almost negative 1.3. So extremely metal poor when you're thinking about planet formation.
Right.
Just to give some context, most of the planets that we find are around, solar or
Yeah.
more metal rich stars.
Mhm.
Basically, we haven't detected really any planets below around negative 0.5. So by probing this area, we're really going to be able to start to ask this question: where does planet formation begin? And
What
so if you look at figure 1,
figure one is good. Figure one, surface gravities, effective temperatures. Yes.
yeah. So this is what our sample looks like. So in purple, you'll see the complete sample of 16,000 stars. And we weren't able to get all the stars that we had in that sample just because we didn't have any test data for it. And we were primarily using the primary mission data. So,
Yeah.
and not all of that even had been looked at yet. So we basically weren't able to complete this sample, but we were able to get 11,000 stars,
Yeah.
which is pretty good. And so from this, we were able to go ahead and get the data. And what you'll see here is that basically this nicely sampled our complete sample. So it wasn't like we were only specifically seeing, a certain type of star or certain basically certain types of stars as opposed to others. So we were able to get basically the full range of stars here.
Right. So the two distributions here are very similar in shape,
Mhm.
not in amplitude because there's less stars, but yeah, the distribution,
Exactly.
very good. Okay. I'm with you.
Yeah. So from there, we had to actually download the data. As you can imagine, 11,000 stars is quite a bit of data. And not all of that data had 2-minute cadence data available, which is,
Oh,
so we had to rely on the FFI data. So what we did is we used the software called Eleanor, and I'm pretty sure it's pretty famous now. It was created by Adina Feinstein, and she's phenomenal. But yeah, but so anyway, so we used this software called Eleanor to basically extract light curves from the FFI data that was available.
okay.
And so what we did here is we basically tried to figure out what had the best data quality. And for each star, that would look a little bit different because you would have maybe, maybe the PCA
Oh, right.
looks better than the correlated flux,
Okay.
for example, or the PSF flux look better than the PCA flux. So for each star, basically, we decided to select whichever data looked and had the least amount of noise.
There we go.
So we didn't specifically look at it because that would absolutely be a nightmare.
Forever.
But yeah, so this was quite automated. So we were able to look at the noise of these light curves and then basically download that specific light curve data, that specific flux.
Cool.
So
Cool.
Yeah. So once we ended up having that, we did some more additional cleaning of these light curves because it's very difficult to find planets in just basically raw data or raw light curves. So we ended up needing to do some noise removal and something that we would call detrending. And this helps us actually detect planet transits. So basically, we end up detrending the light curves using this software called Wotan. And within their paper, they found that the Pawtucky's by-weight method was the best detrender if you just want to do a large number of blind detrending. So, for a specific star, it might be a different method that would be a bit better. But since we were looking at a large amount of stars, we went with what was considered to be the best.
Good.
And specifically because we're looking at halo stars, we wouldn't expect a lot of activity or anything like that within the stars. So it was a very good method, at least for us, to do that.
Good.
And so within the data gaps that there are within, the test sectors, we also had to account for some of those peaks and, falls within the light curve. So sometimes Wotan wouldn't be able to completely get rid of those. So we basically did some sort of sigma clipping at the ends of the light curve, basically where the data began and ended.
Yeah.
So, so basically to get rid of this and make it look like a straight line, essentially. So our transit search didn't say, oh, look, there's a planet here. And in fact, it was just like a data gap.
Right.
Yeah.
Very good.
So we ended up doing that. And we actually used two different transit search algorithms. We used transit least squares, or TLS, which is or was at the time when I started the project. It was a brand new transit search algorithm, and I might be telling on how long it took the paper to get published at this point. But yeah, so we were using that, but we also wanted to use Boxley squares because it's a commonly used transit search algorithm, and it was, it had been used by the field. So we wanted to basically compare how well these two performed together, specifically for halo stars, because in the paper the TLS paper, they were specifically looking at Kepler data. And so we wanted to make sure that before saying, oh, we're only going to use this new method, that it does still work really well for test data as well.
Good. Okay.
Yeah. So from there, we ended up going, so we basically had to figure out how to compare these two methods, and we ended up using, signal to noise and a likelihood method. But basically, once we sent our planets that are light curves through these detection methods, any of the planet candidates that we found, we actually sent them through Eddie Vedder Unplugged, which is this really long bulleted list. But basically, they ended up using, so this was made specifically for Kepler. And so this Eddie Vedder Unplugged was actually updated to run with transit least squares. And this is to help basically vet whether or not these planet candidates are false positives or not.
Yeah. Okay.
Yeah. So they go through a whole bunch of different tests. So they've got a flux contamination test, outlier test, even odd match test. Basically, all of these things
Yeah. Okay. Yes.
Yeah, basically all of these different things to try and make sure that the light curve that we're looking at is not a false positive immediately, because sometimes you'll look at these light curves and they'll look really convincing and you're like, I found a planet, and
oops.
Yeah, it won't be once you start doing observations. So you don't want to, you definitely want to weed out any false positives. So basically we would put the planet candidates through this. And then any planet candidates that made it through this Eddie Vedder Unplugged, this vetting software, then we would actually go into doing follow-up observations. And so we did end up finding a couple of candidates, which was pretty cool. Unfortunately, though, after we did some follow-up observations, turns out that they were not planets.
Okay.
Unfortunately, it would have been a very cool, very different paper. I think if we had to found some of those, that would have been a very, very interesting thing. But I think here we weren't really expecting to find a lot of planets. And if we did find one, that would have been absolutely, it would have been very, very interesting. And it would have been able to confirm or deny some of the theories in terms of how much metallicity is required for planet formation. But yeah, so we ended up doing some follow-up. We did RV follow-up, speckle imaging, and basically they turned out to be eclipsing binaries, or one of them we basically didn't have the sensitivity to confirm or deny. So it is going to eternally be in the planet candidate, probably not a planet stage. Yeah.
Well, I don't know about eternally. Somebody will take a look at it at some point. So.
Eventually, yeah. If we end up getting another, telescope that has much better sensitivity.
That's fair enough. Yeah. And the field of view. Yeah.
Yeah, exactly. But yeah, so that's what we ended up doing with the real data. But in order to actually figure out the occurrence rates, what we need to do is we have to determine our detection efficiency. So the likelihood that our pipeline specifically can detect a planet. And then we have to determine our completeness, which I'll get to in a second. But the way in which we get to this crucial component in determining a planet occurrence rate is by doing planet injections. And so this is the section where we call it the planet injection pipeline. So basically what we do here is we take all of the light curves that we have, and we end up injecting synthetic planet signals into each light curve, and then trying to recover them using the same pipeline that I talked to you before that detrims the light curves, does the planet searches, and then basically we figure out, since we know that there are planets in those light curves, we are able to figure out what percentage of those planets that we're able to find for a given radius, and period.
Mm-hmm. Mm-hmm.
So yeah, so what we ended up doing is we did these planet injections, and we did it for a particular range. So you'll see here these equations, but basically we uniformly drew for these parameters, period, radius, the mid time, as well as the inclination of the planets. So basically we wanted to make sure that we're injecting planets that we would be able to recover, but varying their properties. And so for each planet for each star, we did on the order of around 100 planet injections per light curve.
Okay.
Which ended up being, around 2 million or something when everything's said and done. So a lot.
Right.
But yeah, so we did this, and since we were looking specifically for hot Jupiters, we were able to assume an eccentricity of 1, because once you get that close into your star,
zero.
Sorry. Yeah. I don't know why I said 1.
1. Wait a minute. 1 is it's gone.
I know.
Zero.
Yes, 0. I don't know. I think I was looking at a 1 in the paper, and then but yes,
here it is.
0.
We explicitly
it says it. I was like, wait a second. But yeah, no, it says it.
All good.
Listen to the paper, not to what I'm saying.
Listen to what you're saying.
So we were able to assume an eccentricity of 0 because of this, because of the strong orbital circularization. And so and so basically what we did is we did everything that we would do for the planet, for basically the real data, in order to determine, what our detection efficiency is. And if you look at the next figure, so it's figure 2.
Here's our detection efficiencies.
Yes, this is our detection efficiency. And so what you'll see here is the detection efficiency. And actually at this point, we're able to compare how TLS and BLS do for halo stars, specifically for metal poor stars.
Right.
And so our detection efficiency was actually pretty good. So for So for the hot Jupiters, we were able to get around an average of 70% or so. So if you're looking at 1 on the radius on the y-axis to around 10 days, that would be around 70% average. But in some areas, we had better detection efficiency, some areas a little bit worse. And it was kind of interesting to see here that TLS does a bit better than BLS. So it does a bit better, and which is really, really nice. So it was basically like a sanity check for, using this in the future. And just a spoiler, because of this, we were like, for the next project, we're only going to use 1 now. And
spoiler
TLS does better. We decided to go with that. So this is what we got for our detection efficiency. Nothing too fancy, but it was a nice sanity check.
It's important. Yeah.
Very important. Yes, it's very important, specifically if you want to determine occurrence rates.
Correct.
So from there, we were actually able to get our completeness. And so what the search completeness is it's this detection efficiency that we found, as well as the geometric transit probability. So what the geometric transit probability is basically it just says the likelihood of a planet being in an orientation around its star that we would actually be able to observe the planet transiting. So as you
Okay.
can imagine, basically what this ends up imposing upon our detection efficiency is that for closer in planets, they're more likely to be in an orientation where we can see it transit. And as you get longer and longer periods, the less likely you're going to be able to see a planet transiting. So we have to account for this. Otherwise, we would end up being our occurrence rates would end up being much higher
Right.
than what we would expect. So, and so what you'll see in figure 3, and I won't hover on that too long because it's not so much fun, but basically this is just looking at the search completeness that we found, and this tells you the probability of detection for a specific period and radius of a planet. And as you can see, the further out that you get, even though we had pretty good detection efficiency for those close in hot Jupiters, it still goes down to about 24% at best. So yeah, so this does a lot.
And down here at the radius of 1 period of 10, it's in the few percent range.
Exactly. So this has a large effect. That's why we need to take it into account when we're doing these occurrence rate studies.
Cool.
And so, yeah, and this is basically just based on the planets on the star radius and semi-major axis, and you get this basically.
Yes, that was equation 2. There we go. Yep.
Yeah.
Yep.
And so once we had that, we were actually able to start getting at these occurrence rates.
Okay.
So what we ended up doing is we basically followed what some previous works did. And because when you're looking at these really extremely close in planets, as well as these more massive planets, you're able to actually use a simpler version and use the binomial distribution to determine the true frequency or true occurrence rate of planets, which is very, very nice.
Yeah, very cool.
Yeah. So basically we take this equation 3, which is the binomial distribution. And since we had 0 detections of planets, we were able to basically sub-zero in, and the equation actually ends up becoming very nice. And you'll see, I think it's equation 6.
Yes.
So after you do a little bit more math, or equation 5, sorry. After you do a little bit more math, you end up getting this upper limit of the occurrence rate. And all this depends on is your confidence interval. So, you can choose 1 sigma, 2 sigma, 3 sigma. For ours, we ended up going at the 1 sigma level in line with previous works, basically for comparison's sake. And you also need to know this in here, which is the basically effective sample size or the total number of stars in your sample. And so here, equation 6 is basically the effective sample size, because we don't have, if you look at the completeness map, we don't end up having 11,000 stars that we can say are in each bin. That's not what we're able to look at, because we're only 24% at best are going to be oriented in a way that we would be able to observe them.
I'm with you.
So basically we have to account for this. So we end up taking the total number of stars that we have, and then we multiply it by the probability, the geometric transit probability, as well as our detection efficiency. So basically those two are the search completeness. And so that ends up being our effective sample size. And so our effective sample size was somewhere around the 600 stars. That was the average effective sample size, I should say.
Okay.
because for each bin it
Bin.
varies.
Yeah.
Mhm.
Mhm.
So, so anyway, we were able to do this, and then we were able to get the effective or the upper limits of planet occurrence rates here. And that's the big money plot that you'll see. And so,
Should we go there?
yes, we should go there for sure.
Let's go there. Upper limit. Here we go. Ooh.
Yeah.
Ooh.
So you'll notice that we have different upper limits for different, for different bins. So basically we've got 0.36 as our lowest upper limit, and our best upper limit is 0.04.
Okay.
And so, but the average upper limit was around 0.18%
Okay.
for planet occurrence rates,
Okay.
which is extremely low. To give some context, around a solar-like star, it's around 1%. So it's not absolutely terrible for hot Jupiters, but
It is low.
it's definitely very low. So, and
Okay.
so, yeah, so basically, do we expect to see any sort of hot Jupiters in this regime?
Yes.
No, not really, because of,
Right.
yeah, we would need to look at so many stars to even find one if it was there. So,
Right. Okay.
but yeah, so this is basically kind of like the big thing that we found. But when you start to put this in context of other works, which we did in the last table in the paper, you end up seeing that basically, if you look at the last three, so there's Mortier et al. 2012, as well as Sazzetti et al. 2019.
Okay.
What you'll notice is if you look at N and FP, these two columns,
Yes.
we had the highest effective sample size. And we were able to put the best upper limit on planet formation within this metallicity range of -2 to -0.6. And so this is really exciting because we were able to do this using the transit method, and there's been a bit of contention about the transit method versus RV just because of the selection biases and whatnot.
Yes.
But here it seems to be in line with what you would expect, particularly given that we ended up doing almost something very, very similar to these previous works that we can directly compare to. And here the effective sample size is the main driver of having a better upper limit for your occurrence rate, along with the detection efficiency, of course. But that all falls out of, our effective sample size falls out of all of those things that we take into account.
Right. Equation 6.
Exactly. Yeah. And so for, when you start looking at different metallicity ranges, you end up seeing on this, on this table that the occurrence rates tend to go up with, higher metallicity, which is something that we would expect.
Yeah.
So this is very much in line with previous works, and
good.
And ours is by far has the lowest metallicity range of any sample so far. Yeah, you can kind of just see the metallicities go down a bit. But yeah, even the ones that we can directly compare to the Mortier et al. At 2012, as well as the Sazzetti et al. 2009.
Right.
We still have a lower metallicity range. And so yeah, so this was really interesting thing to look at. Another interesting thing to look at here, or to kind of point out, is that we know that for metal poor stars, some of them can have alpha element enrichment, particularly the ones that host hot Jupiters. So that would be something very interesting to look at. And it's a very important thing here to kind of discuss, because we don't have that,
Yeah.
we don't have that data. And I feel like at this point,
Yeah.
only at this point are we starting to really get these stellar abundances to really be able to say something about planet populations. Because before we only had metallicities, and it's really interesting now to start to see how the field is progressing.
Yeah.
But yeah, so I think that basically what we found here in our paper was that, in line with previous works, it's not super drastic or flashy conclusion, but it's in line with previous works, and
Science.
we expect, yeah, exactly, science. We expect that that the upper limit of planet occurrence rates for hot Jupiters in this regime is less than 0.18%.
Right.
And so you really wouldn't expect to find planets here.
Right.
However, that there's still that 0.18%.
Yeah,
so
it's not zero.
it's not zero. There's still that 0.18%. So it would be a very exciting discovery for sure. But yeah, so I think that here we're starting to see, starting to actually be able to probe these more metal poor regimes. And I think that this was an exciting paper for me. And I think that a lot of people were actually really interested in this paper because basically up until TESS, there weren't very many papers that were looking at this, but people have been very interested in it. And I think since this paper has come out, we've started to see a lot more research in the field trying to kind of get after this question of what happens when we don't have a lot of material to form planets.
Right.
And so, yeah.
When does it begin? Well, that's awesome, Kiersten. That makes you a pioneer here if there's a lot of work going on. So very cool. Very cool.
Thanks.
And thank you so much for walking us through your very lovely AJ article. And you touched on it a little bit there at a couple of points. So let me go ahead and push on it a little bit because this was paper 2 in the series. And so where do we go from here given the published article? And this was 2021 and we're 2023 now. So maybe there's been some progress, Dr. Boley. And so it's just sort of where do we go over, let's say, the next couple of years on this topic in order to determine, I think, the primary question of when does planet formation start as a function of Z, for example.
Yeah.
Is there new observations coming or already in the pipe? Is there paper 3 in the pipeline? Is there additional theoretical models? Just sort of where do we go?
So it's actually really exciting. So there are 2 papers in the works, actually. So one specifically revisiting these halo stars. And I didn't mention it too much while we were going through the paper, but we actually had good enough detection efficiency for these other types of planets, these smaller planets. So sub-Neptunes, mini Neptunes, sub-Saturns, mini Neptunes, and super Earths. And so one of the things that we wanted to look at was actually what do the occurrence rates look like there? Because we did have a couple of candidates in that regime. So we were doing some follow-up observations on those. So basically revisiting this was one of the things that were in the works. That paper is in the works. Cool. And then also a very exciting paper that I've been working on over the past 2 years with Jesse Christensen is looking at a slightly more metal-rich regime. Okay. So we have a sample of around 100,000 stars for, yeah, I know, it's huge. It's a huge sample compared to 11,000 stars.
This comes from TESS?
Yes, from TESS.
Okay.
Yeah, looking at this more metal poor, just slightly more metal rich to see if we can start to see this like cutoff where planet formation actually, starts to decrease.
So
And
you look low and you don't see it. So what if I go a little bit higher? Well, I see something. Yes.
yeah. And so this paper, it is written, and it is a very, very exciting result. Not to have too many spoilers, but we think that we might see something.
Cool.
And so that's a very exciting paper that I'm super excited to submit. We wanted to make sure to triple check everything. And now that everything's been triple checked, quadruple checked, we're like, I think this is a result. So
nice.
Yeah.
Well,
so
that's a teaser if I ever heard one on one of these.
I know.
AAS journals, right?
Yes, I think so. At least that's what the template is in. So,
good.
But yeah, no, I think that those are the things that are exciting in the works, and should definitely be able to see soon. And I'm really excited to do even more and see, how much of these stellar abundances as well, because that's another project that I've just started that I'm really excited about.
The alpha enhancement, for example.
Yeah, exactly. So yeah.
Very cool. Very cool. Well, that's quite a teaser, and I really look forward to seeing this field advance over the next couple of years, Dr. Boley. And yeah, it'd be really great. So thank you so much again for walking us through your very lovely article and where we're headed with this topic. So good.
Awesome. Thank you so much for having me.
Sure. Thank you. And that'll do, everyone. And I hope this makes your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.